For this problem, 7132, it's given beta, it's 100. Okay, and in part A we need to find the collector current and the collector voltage. So in this circuit here it's an emitter follower, so we have 0.5 milliamps flowing here. Those 0.5 milliamps is split here at the base and here at the collector, and they group again to form the emitter current. So from this analysis, from the DC analysis, one thing first, this one here, these capacitors, they behave as an open circuit, so those small signal voltage source and the load resistance here, they are taken out of the circuit. Okay, and from this first analysis in green, we know that IB plus IC is equals to those 0.5 milliamperes, and we know that IC plus IB is the emitter current. Okay, so those 0.5 milliamps are actually the current that's flowing here at the emitter. We also know that this emitter current is equals to beta plus 1 IB. So we can calculate the base current, and that's equals to IE divided by beta plus 1. So this gives us 4.95 microamperes. So we got IB. And another thing is that because we know that this current here, IE, is flowing through these 200 ohms, we can calculate VE, right? So VE is equals to those 200 ohms times those 0.5 milliamperes. And this gives us a VE that is equals to 0.1 volts. Now if we assume active mode operation, we know that VBE, because it's an NPN transistor, VBE, that's equals to VB minus VE, is actually 0.7 volts, right? So between base and emitter we have 0.7 volts. Now we know VE, right? So if we know VE, we can calculate VB is just those 0.7 volts plus that 0.1 from VE. And this gives us a base voltage of 0.8 volts. And if we know the base voltage, we can now calculate the collector voltage, because we know that here at this terminal we have VC, right? This is VC. So, or let me draw it here. So here we know that we have VC because it's directly connected to the collector, and here we know that we have VB, and here is the base current, IB. So we can calculate VC by, if we take VC minus VB, that should be equals to the base current times the base resistance. And this gives us a VC of VB, okay, so 0.8 plus those 4.95 microamperes times those 200 ohms, and this gives us a VC of 1.8 volts. So let me just verify. So those 4.95 e to the minus 6 times 283. Yeah, that's roughly 1 volt. This one here. Plus those 0.8 gives us 1.8 volts. And now if we know the base current and we know beta, we can calculate the collector current, right? Because the collector current is equals to beta IB. So IC is equals to 100 times those 4.95 microamperes, and this gives us a collector current that is equals to 0.495 milliamperes. Okay, so we defined those two quantities that we needed for part A, VC and IC. Now for part B, let me go down here. I have like several copies, but we need to use the T model to obtain the overall voltage gain. So we need to, now we are going to perform a small signal analysis. So we need to define the parameters for the T model. And now all the DC voltages or current sources, they must be either short-circuited or open-circuited. So because we have this current source here, it becomes an open circuit, right? So we just take that current source off. This capacitor, it becomes a short circuit. This one here, it also becomes a short circuit. And then we substitute this NPN BJT here by its T model. And if you remember, the T model is just a current source here with this is the, so this is the emitter, this is the collector, and here is the base. Okay, and this is GM V, call VE, which is this voltage across RE. Okay, and for these parameters, we know that RE is equals to the threshold, so sorry, the thermal voltage. I'm confusing with the T from MOSFET. So it's the thermal voltage, capital T, divided by the emitter current, and that's equals to 25 millivolts divided by the emitter current, which is 0.5 milliamperes, and that gives us 50 ohms. Now for GM, the transconductance, we know that's IC over VT, and that's equals to those 0.495 milliamperes divided by those 25 millivolts, and this is 0.0198 milliamperes per volt. So we got those two values, and then if we substitute the BJT by its T model, that's the circuit that we get. Okay, so I have several copies of it. And now we need to analyze this circuit to obtain the overall voltage gain. So first thing is that, well, let me be concise. So I just told you that this is VE, so let's call it the same way as it is in the circuit. So VBE, VBE here. Okay. So if we want to obtain this voltage VBE, basically at this particular node here, we know that we have VI applied. So if we do like a loop analysis here, we can see that this voltage VBE is actually a voltage divider between RE and the resistor of the emitter, right? So we can write this VBE as VI times RE divided by 200 plus RE. So that's VBE, which is this voltage up here. Now if we look at the current that is flowing through this 200k ohm here, that's the same, so let me call it I 200k. That's the same as, because we are assigning this direction here for the current, it's the same as the potential here minus the potential here divided by 200k. This potential here is V naught minus this potential here, which is VI, divided by 200k. And we also have an equation for V out, that V out is equals to the sum of this current here plus this current here, right, minus the sum of those two currents times the load resistance, right? Because the current that's flowing here through this 20k is actually the sum of this current here, GM-VBE, plus this I20k, 200k here. So, and because it's going in the opposite direction as the plus or minus assigned here for V out, we have minus GM VBE plus I200k times the load resistance, right? So that's the equation that we have. Now if we plug in VBE here and I200k here, we can obtain this equation here. So V naught equals to minus GM times VI times RE divided by 200 plus RE, right, that's VBE, times the load resistance minus this current here times the load resistance. So it's V out minus VI times the load resistance divided by 200k. Now if we expand this equation here and isolate V out, okay, so we can start doing that. So I will start substituting some of the values. So V out is equals to minus GM VI RE RL divided by 200 plus RE minus V naught, and then we know that, so V naught RL divided by 200k plus VI RL divided by 200k. This we can see that, well, this term here, it depends on V naught, this one here, it also depends on V naught, so we can group them both on the left hand side. So it gives us V naught times 1 plus RL over 200k, and that's equal, so now we have VI here, VI there, so we can group VI. That multiplies the first term here, it's minus GM RE RL over 200 plus RE plus RL divided by 200k. And now we can basically obtain the overall voltage gain. That's V out over VI, and that's the same as those. So if we start like substituting values here, so this term here, it's 20k divided by 200k, so it's 0.1 minus GM, that's 0.0198 times 50, that's the emitter resistance, small signal resistance, times the 20k from the load, divided by 200 plus the emitter resistance, which is 250. and everything here divided by this term here, which is 1 plus this term here is the same as this one here, so 20k divided by 200k is 0.1. And if we solve this equation here, we know that V out over Vi is equals to minus 71.9 volt per volt. And that's the final answer for part B.